So, welcome everybody, and welcome to this hopefully last podcast for 2AA for this term. We're gonna look in this podcast on code quality management and more specifically management of how to improve the quality of your software and how tooling can be used to support this. So first, we're going to look at the software quality, like the notion and the definition of software quality. Then we're going to look at the static code analysis, how this kind of technique can be used to support this. And then we're going to look more specifically into rule-based systems and rule-based systems that there's systems that you're going to use and experiment in this week tutorial, which is named SonarQube, and that's also what you're going to experiment during the next assignment. So first off, software quality. We've discussed a lot, and we've kind of experimented a lot about failure. Remember, embrace failure, fail early, fail quickly. That was basically the very idea of agile development, so that you can assess what happened during the failure, find a way to improve, and based on this improvement, make a better version of the software and a better version of your team, thanks to a new set of practices. That's what we experimented together in the paper plane factory, for example, where we were trying to fold the plane, not really good the first time, then improving, and then the second time it was better, and so forth. So the first thing is that we need to keep this in mind. Problems during development, it's frequent, it's inevitable, and that will be expensive. That will be really, really expensive. So we know that those problems can exist and will happen in during the development of a software product. So we need to deal with it. We need to find a way to live considering that as part of our engineering activities around developing software, we'll encounter a problem. This is inevitable. It will happen often, and that will be expensive. So really with this in mind, we need to counter the notion of failure as something like as a first-class citizen. It's totally okay to fail as long as we know to react and as we find a way to react to the failure. Of course, if you're building a plane, you don't want to fail when the plane is flying. That would be a catastrophe. So you want to fail early. You want to fail at the test level or the requirements level so that you can get all the problems identified way before they happen. And this notion of failure is so important that there was kind of surveys in IT companies, and the results are kind of daunting. If you look at the result, you'll see that out of more than 10,000 projects, which is kind of a lot for a survey, only 2.5% considered that it was a success. 2.5% out of 10,000 considered that the project was a success. And for all the others, they said that they have failed to meet original targets and they've missed the budget or they missed the deadline. Okay, so all of those things are kind of triggered into failure. And even if you restrict to one single company, for example, and you look at IBM, which is supposed to be not such a bad company, well, you see that only 40% of the projects have kind of a success rate that makes sense. So that is something that is really, really important when developing, and it doesn't really happen to others. It happens to everyone. And in the very same survey, you learn that 17% of the projects were so bad that they've jeopardized the company. Okay, so it can go really, really wild. And that is the way we react to failure as software developer and as software engineer is really important, because that's how we can be sure that the product will be delivered. Maybe not the ideal product, but something that is running, that is consistent with a good level of quality, that is okay for the way the people are going to use it. And more globally, all these activities, it's kind of set into what's called software maintenance. Okay, basically at some point we start here with a given product, and this product is kind of modeled. We have blueprints, being class diagram, sequence diagram, state diagram, MIS, ADT, like whatever kind of things you can use to specify and design describe your product. This is part of the kind of like forward engineering. And out of this, we obtain kind of like a version of the product. But then remember the definition from Google, the software engineering, it's programming integrated over time. So basically your system will drift, okay? Initially, when you're developing it, that will be quite close to those blueprints, but you're going to add features and features. And remember the entropy problem, the fact that your software will tend to go into chaotic mode where a lot of features entangled and stuff like this. And so if you take this very version of the system, which is a running one, and now you try to kind of like extract the information and reverse engineer instead of forward engineer, you'll find a product that is different from the product you have initially. That's a problem in terms of engineering, okay? Because from programming point of view, that's fine. But from an engineering point of view, we had something here, and basically through the cycle of development, we end up with something which is not what we thought we have. So it's like we've built a bridge, and the bridge has some kind of like capacity in terms of trucks and cars. And actually the running one, the real one, the one that was built, is different from what we have on the blueprint. So that could be a catastrophe. In this case, so in this notion of maintenance, we're talking to basically four kind of different maintenance. We have the corrective maintenance, the adaptive maintenance, perfective, and preventive. And all the kind of things that we're doing together are really related to finding a way to develop software with a good level of quality that will support this maintenance, to correct bugs, to adapt to evolution, to improve performance problems, for example, or to prevent those problems to happen, okay? We'll go a little bit we'll dig deeper into the maintenance problem in the next lectures. This one's just like a global overview, but that gives you like perspectives. Where are we going? Well, we're trying to consider software as a whole over time, and we really want to have a level of quality that support those kind of things. This was the notion of quality that is kind of like the foundation of all this work was theorized by McCall in the 70s. And there's basically several dimensions, like for product to be of good quality, needs to consider its maintainability, its reusability, interoperability, correctness, efficiency, integrity, like all those kind of different dimensions and factors that are important. But what is really important is not those terms like known by heart. It's really the fact that this goes kind of like a pyramid, okay? So we have here the notion of quality, which is like our goal. We want to deliver software with good quality, but good quality by itself doesn't mean anything, okay? It's just like ideal that is non-really quantifiable and that you can't really measure. So first, the breakdown is about factors. So when we talk about quality, are we talking about reusability, maintainability, portability, testability, integrity, correctness, like all those different factors? Okay, so let's take, for example, maintainability, because that was our objective on the previous slide. I want to develop software. I would consider my software of good quality if it is maintainable. And then, but this is still like non-measurable. Okay, this is something that, okay, this kind of like an ideal objective. So how can we really focus on maintainability? Well, the maintainability will go like for the way it's structured, for the way it's concised, for the way it's legibility, self-description, and all those kind of things. You see, so we can take like this maintainability factor and break it down into criteria. And then for one given criteria, we can go into a finer grained level and we can start to measure. We can say that, okay, so the way we measure the structure will be related to the number of methods, the number of parents, to the length of the method, and stuff like this. Okay, we'll go a little bit bigger in this in the next slide. But this is to give you like a grasp, like an overview of, we start here, our global objective is here, that's quality, and we end up there by finally measuring stuff like the number of method, because we're following that path that goes from the quality to the metrics that support it, okay? So this is how this theory will support us into kind of like having confidence that the software we're developing is of good quality because, well, based on those metrics that fill those criteria, contribute to this factor, well, we're contributing to the global quality of the software. And the global ID, which is behind this, is really like you can't control what you cannot measure, okay? So you really have like the global ID of, we have the ideal objective, quality, maintainability, reusability, and we break it down into things that we can measure because those measure, it's like using like a thermometer to get the temperature or using like any, like a speed gauge on a car to get the speed. That's something that we can get. It's a number, and this number we can measure, and we can also like compare or stuff like this. So that leads us to the second part of the of this presentation and of this course, this lecture, which is related to static code analysis. Now, we have the idea that to maintain good quality of software, we'll have to kind of like be sure that what we're doing contributes to those factors. And to have these factors, well, we're gonna basically start to measure stuff, and we're gonna measure stuff in our source code. So that's basically what is encountered by static code analysis. So the whole objective of static code analysis is, well, not necessarily the objective, but what's classically used would be for maintenance and corrective maintenance. So there's a way to use a program that will take a program as input and will try to kind of like explore it, okay? So this is not helpful for design, but this is like considering this program on the left, are we sure that it is safe to execute it? Will not have like any buffer overflow, will not explore real space in memory, will not crash. Can we anticipate such kind of error without having to execute the code, just by looking at the code and looking at the space the variable and the program is going through? This can be done with static analyzer. So this is this slide, and this example is extracted from a tutorial on abstract interpretation. Abstract interpretation as one among other technique for static analysis. And basically what we have here is that for each instruction here, we're attaching a state. Sorry about that. So for each instruction here, we're attaching an annotation, which is in orange, that represents the state. So in this case, we know that the variable n0 will be greater than 0. And then by combining all those things together, we know that variable I comes from n, and n is also dependent of n0. So we can analyze this kind of like control graph that transfer this information to kind of like restrict the space. And by combining all those different intervals, we're basically building a polyhedral model of the space, like the real space, a multidimensional space of all the different values that the variable can take, which gives us those possible trajectories here, which are like all the different paths that the execution of a program can take. And by having this, by modeling this space, we can basically try to avoid, let's say, places in the space that would be forbidden. That would be a safety problem in an embedded system. You would run out of memories. That would be a buffer overflow. That would be like whatever kind of safety criticality that you can ensure. What you know is that your code should never be in that state, because that would be a crash, or this code should never be in that state. That would be a crash, okay? And by using static analyzer, you can check that all the different trajectories, which are the lines, never go to the red zone. So you can kind of like prove that the very idea of those approach, prove that you're on track, prove that the quality attribute that you're looking for, they will happen actually. The quality is supported because you're not going to go based on your analysis of the code into those red zone. This was done, for example, at the C level, the C language level. You have the Pharmacy toolset and the Concert compiler, which are kind of like subset of C that was kind of like proven and that support those kind of mechanism. And actually, if you take a little step back, by using the static analyzer, you can do stuff that are kind of like super fun, like automated program repair. This is kind of like a digression with the with the topic of the lecture, but still this is related in a way to find improve maintenance and improve like bug fixing on open source software. There's approaches like Ripinator that was published by KTH and INRIA in north of France that are basically crawling GitHub to identify bugs. Okay, and when they have a way to fix it, because they by analyzing the source code, it's like, oh, that's a kind of bug we know how to fix automatically. They basically create a patch and made a pull request that is sent to the developer saying that, hey, we fixed the bug. And finding those kind of bug, the kind of bug that you can automatically fix is kind of like tricky, but assuming that you can do, these can end up by those kind of patches being merged with the source code. So this can be helpful to the point of helping people resolving bugs at scale, like working on the whole GitHub database and GitHub project, which is kind of like awesome. But that being said, although the approaches that go through the code and try to kind of like interpret it or find where the program can go are like reaching a glass ceiling at some point, which is named the halting problem that you will encounter in your advanced data structure and algorithm classes. So we're not going to dig into this right now. Basically, that what we know, and just like a very, very short and kind of like not almost correct version of this problem, but that was okay for 2A4, would be that finding all possible errors isn't decidable. So there is no algorithm that can take a program and find all the errors out of it. Okay, that's very same for the halting problem. There is no algorithm that can take a program as input and tell you if it's going to stop or not. That is the very problem of the halting problem. So all of the approaches that use static analysis, they're basically stuck at some point. They can give you stuff, they can approximate the truth, but they're not really able to work at scale. So what's done in this context is then like, okay, we can keep the ID, we can keep the point of we're going to analyze the source code without trying to execute it. The next two lectures will be about how to find errors while executing the code. This lecture and these approaches based on static analysis are like, we're not executing the code at all. We're just like looking at the code. And so instead of trying to interpret where it's going, we're going to take a very, very simpler approach like static code analysis for the poor, which is let's measure. Okay, because within the quality attributes, they're really about measuring stuff that contributes to factors, dimension, and then quality. So what's a measurement in that context? Well, that's basically just quantifying something. Okay, and this quantification, this number, well, we can use it to compare. Like I have more X than this other program. Is it good? Is it bad? I don't know. It's just like I can tell that I have more or I have less. To perform those measurements, we need instruments. And in software engineering, those instruments, they are named metrics. A metrics, it's a function. Okay, it's not a number. The metrics is the function that take the program and produce a number. Okay, so metrics is here to produce measurement. Metrics can be number of method, number of whatever, but still the whole point is that you apply the metrics to the program and then you get the number. And the software metrics, it's basically related to software, okay? Because metrics and measurements, that's kind of like international in terms of measurements. It's not really domain specific, but in our case, we have kind of like a taxonomy of all the different metrics that make sense from software. And it's not only on the code, actually, it can be on the processes, can be on the documentation, can be on like all the different artifacts that are involved in the definition of software. When talking about metrics and measurement, the main thing is consistency. Okay, you can't measure things that are measured differently. So would it make sense to compare the number of methods in a functional programming approach or procedural programming approach or object-oriented approach? Not necessarily. Even if there's the same element, like the number of methods, as the paradigms are different, it might not mean the same. So when trying to compare, you don't want to be comparing apples and Wednesdays. You really want to compare things that make sense. So in our case, what we usually do, at least at this level for 2AA4, is working with the metrics on one single project and seeing how the metrics evolve over time. So I'm not comparing my number of methods with any other Java project. I'm just looking at how it evolves over time in my project. And is it going in the right direction or is it going in the wrong direction? To compute those metrics, there's tons of software available. One that I'm often using is named SCC because it's one of the most efficient and versatile. It's written in Go, like goes super fast. You can analyze gigabytes of code in seconds. So that is pretty cool. And it's also multi-language, which is pretty practically interesting. So in this case, I took the source code of JUnit, which is the test framework you're going to use this week during the tutorial. So that was kind of like accurate. And I just asked SCC to compute, like, give me all the metrics that you can have. SCC is like very limited in terms of metrics, but kind of like works on any language. So what's SCC is computing is the number of files, number of lines, number of blank lines, number of comments, the number of lines of code, like the number of statements, and what is the code complexity, okay? And the code complexity, it's really, well, an approximation of how complicated is your code, okay? It doesn't mean anything per se, but that's kind of like the higher it is, the like weird it looks for your program. But we're not going into that level of detail, that really fine grain, because SCC is multi-language. It's like Git. Git can merge any piece of text. So that's cool, but sometimes the merge is stupid because it doesn't respect the like Java or Python convention. That we're saying here. SCC can count like number of lines of code, number of comments quite easily, but more than this, it's really not. You need something dedicated. And on a piece of software, you can be like, okay, let's count number of method, number of attributes in an object, number of lines of code, number of statements. If you have an object-oriented program, number of children of a class, for example, that can give me information about the structure and stuff like this. But what you really need to take and to take in mind and to keep into account is really like, those are numbers. And you can't really do anything with numbers, okay? They're really not interesting. So those numbers and those measures, we know that now we can analyze statically source code to extract those numbers, but we need something to build out of it, okay? We need to create something out of it. And this is how rule-based systems are going to help us. So we're going to use static analysis, like the counting I've just shown you, to extract numbers, and we're going to combine those numbers together in a way that gives us feedback in terms of how good or bad our software is. Be careful, those systems and those rules, they're stupid, okay? They're just like taking a number, applying the rule, giving an answer out of it. It's your job as software engineers to interpret those rules. Sometimes there's a violation in the quality gate, and that makes perfect sense for your context. Sometimes your software is terrible, but it's written in a way that hides the fact that it's terrible for those rules. Sometimes on purpose, sometimes not on purpose. So be really careful that when you're using those systems and all the kind of things that are going to be presented in the next part of this lecture, you're basically looking at symptoms. Okay, you have someone that comes to your practice and say, oh, I'm coughing. And now your job is to take into account the comprehensive assessment of the code to understand, why is this person coughing? Okay, why is this code bad? Is it like very light, just like, okay, you just like have dry hair and everything's fine? Or is it something which is way more complicated, like way more serious, that requires maybe surgery or whatever? Like in our case, surgery would be refactoring or would be like getting rid of some part of the code. You just get the symptom, okay? You're still like, oh, there's violation here. And how do I fix it? It's your expertise as engineers that will help you to fix it. In this course, we're going to look at two tools that are presented in this lecture, PMD and SonarQube. SonarQube is this week tutorial, so that will you will manipulate it. PMD is way easier to use, but more specific to Java. So like SonarQube is more versatile and more used in the industry, actually. And I really like the fact that PMDs, the motto of the tool is don't shoot the messenger, because that's precisely what I was saying on the last slide. Like only symptoms, it's just like bringing you information, and it's you as professional engineer to integrate this into your practice so that you can take something out of it. Okay. So what tools like PMD can do for you, it's basically entering things like code convention, for example. Like you want the code to be readable, that is like good quality attribute. And to be readable, part of the readability is to respect the convention. So for example, there's something that say that, oh, in Java, you can of course write it, but that is not really good. So this is tolerated because that gives you like a one-liner. So if something do this, that is okay. But as long as you're using else statement, then you should have those brackets, because that's convention. Maybe you can find it stupid, but that's how it's supposed to be in Java. So this code is basically not good. And to do this, we're basically defining rules. So the way the rule is implemented can be pure Java, can be pattern matching. In this case, it's using a language named XPath. We're not going to go into the details of XPath, but basically what the rule is saying is that, oh, take a statement, it's an if, and it has an else. Then if there's an else, there should be a block if you're not in the if statement. Okay, the syntax is terrible. XPath was invented in like 20 years ago, and that's terrible syntax. But you get the idea. Okay, it's like I can write a program that detects in my program that there is something wrong. And in this case, I'm in if, there's an else, and I'm not part of the block. So if this is the case, then I'm violating this Java convention. And this can be elevated a little bit more, because this is kind of like immediate. And if you now look at a tool like Sonar, you can have this kind of like combination of things. So we're going to dig a little bit into Sonar, and Sonar has those idea of quality gate that gives you like grades. So for example, this software in terms of releasability, sorry, it's an A, reliability, it's a B, and security, that's an A. Remember, it doesn't mean that it's true. It just means that based on the metrics that have gathered some measurement, and by combining those measurements according to like classical rules, we believe that this is an A, a B, and an A, okay? And we can tell that, oh, there's also like, look, there's a D here. So maybe you should like look at this and fix it, okay? So it's kind of like aggregate those information and provide it to you in a web-based interface that you can click and explore, which will basically be your tutorial this week. And if you look into one given project, which is, so those are like two screens, actually. This is like one global screen on the left, and on the right, that's when you select, for example, one of those projects, you click here, and then it brings you to the next page, which is like the global view of one given project. And when you're on one project, so this is like the name of the project, you can see, for example, that, oh, that's okay, you passed. So based on the regular quality gates that we're using, the way we're combining the metrics for classical Java program, that's okay. We haven't found any bug, okay? But if you look at here, you'll find what's interesting for us, which is the evolution. And what we'll found here is that, oh, there was one here at some point, there was some bugs there. And then it was like totally flatline. And then at some point, they also detected bugs, and it was fixed. And that's the very same for example, the depths, because all the things that we're talking about, technical depth, it's kind of like slightly weird lines of code that can be detected. Not all, like not design depth, like terribly designed code can't be detected by those things because it doesn't work at the design level, it works at the code level. But the little quirks in your code can be identified by those kind of things. And what is interesting here is that you will see that at the beginning there was nothing because, well, the project was starting. Then they had a lot of debts, and then slowly they went back into control and they were reimbursing their depths, okay? So tools like SonarQube can help you measure, at least at the code level, the depth you're reimbursing and how the quality is improving on this dimension. Doesn't help for the design, will not find any design problem, but will help you for the for like just little quirks. So that's why committing often and pushing your code often to the server and running this kind of analysis quite often, that's really critical because that gives you access to those kind of graphs and that can help you gaining confidence in the fact that you're doing the right things. And if we look into one dimension, we can have like very, very simple visualization. There's a course at the end of 2AA4 that will be related to visualization. But if you look at this, for example, we have kind of like a multiple dimension bubble chart. So on the left, there's technical depth, okay, measured based on the rule. Here is line of codes because you can have like terrible code, but not that big, or super big code, but extremely good quality. Then we have the maintainability rating, which is the color, okay, A being green and E being red. And the size of the bubble, it's a code smell, okay, so number of bad patterns that we can find in the code. And what is interesting is that we can find that here, the whole software is more or less here, okay? Each bubble is one class, but we also have some outsider, okay? We have the outsider that are here, and those ones, they're basically like, man, not that bad. Maybe they're kind of like really big in terms of lines of code, the more you go to the right, but there are not that many depths in it, so it might not be such a big deal. But what we can see here is that those guys here, they're kind of like outsider, okay? If you compare those 1, 2, 3, 4, 5, 6, 7, 8, 9, like 10-ish classes, that looks really different than all the others in terms of depth and maintainability and number of code smells, so quirky code inside them. So maybe could be a good idea to look at them. And if you have to refactor, if you have to fix something, that could be a good candidate, okay? But also, if this class, for example, is never used, like it's used once at the beginning of the program, maybe it's super complex. We know it, but we're using it once during the lifetime of the project. So maybe it's not important to fix those problems now. We just need to have them into account, be sure that there is no critical issue in this because that would jeopardize the whole project. But if not, we can live with it. Again, it's just a symptom, doesn't mean that, oh, you have to fix it. It's just like gives you an information of things that might require to be fixed. And you can do the same, for example, like this one is more visible because it's for security. So there's some way of writing code that are violating security rules and this kind of things. You can see here that the whole product is here. So everything's fine, except those guys. And more specifically, this one, which is like totally different from the others. Okay, with like 3 vulnerabilities inside, and this might maybe need to be fixed because this class is named designer, and so that's something that will be used a lot in the project that we're analyzing right now. And so it's kind of like a critical piece of the software that has very, very strong security issues, so would require us to be fixed. So if we consider this in remember, we're developing, but we're also publishing, releasing, deploying, operating. So it's DevOps context. Well, those tools will give you immediate feedback. As long as you have SonarQube installed, it's just like running a Maven or Gradle or whatever command to push the analysis to Sonar, and Sonar will bring you the graphs and show you all the things. So that's really good. You can get the measurements and you can get the quality gate, and that gives you like an A, B, C, D, E grade quite easily. And you can get the tendencies, okay, the way your program evolved. No, totally normal and legit to be in debt at the beginning, but you want to like reimburse. You can measure these reimbursements. What those tools can't do is really first tell precisely what they mean by quality, okay? The quality gate they've defined are based on empirical evaluation of how people are writing Java-ish program and software, but that's it. There's no real science behind it. It's pure state of practice, let's say. And also, they don't work at the architectural or design level. They're really working at the code, which is the lowest level possible because of the limitation of static analysis we were saying at the beginning. Okay, so they can't really do more than what they're doing. Doesn't mean that this is useless. It just means that it's interesting. It gives you information, but it's just part of the information. You should not take your SonarCube website like for a project and say, okay, fix it, fix it, fix it, fix it, fix it, fix it, fix it. Because sometimes to fix a set of small problems, it's not focusing on those three problems that will fix it. It's maybe that the root cause that is elsewhere that you need to fix, and eventually it will fix the other problem. So don't be just like, oh, this is a checklist of things that I need to fix. This is not how it works. It's really like giving you symptoms and you're in charge of analyzing the whole symptoms to provide a comprehensive diagnostic of what's happening and take the right action. Okay, so it's a tool that helps you, but it's not like a tool that dictates you what to do. To conclude, well, software quality, it's necessary to ensure quality. It's common sense, but better to say it. And classical quality models relies on factors, criteria, and metrics. Static code analysis approaches, it's a very, very wide spectrum of approaches, can be go from abstract interpretation where we're defining a polyhedral space of the different trajectory that a program can take. And it can go to kind of like counting line of code. Okay, this is like the same family of approach. So when you're hearing someone say, oh, we're going to do some static analysis, just first refine and be sure about what you're talking about. And even the lowest one, like the counting line of code, that can be helpful actually. Okay, so sometimes to get the answer at scale, it's more efficient to get those coarse grained metrics that just tells you where to look instead of trying to find the abstract ultimate solution that will just not scale on the size of your software. And something which is really important, it's pure vocabulary, but it's really annoying. A measurement is a number, a metric is a function that produces a number. Okay, so when we say that the metric is a number of method, it's not really the number of method. It's the function that produces a number of method. And when applying this metric to the program, you obtain a measurement, which is the number of method for this very program, or this class, or this file, or whatever. And based on all those measurements, what we obtain and what we have is a rule-based system, because we need to aggregate those information together to provide more value to the end user. And the end user in this case, it's you as software engineers / developers. So we're combining all those numbers together and we're identifying symptoms. And I really re-emphasize this here. We're talking about symptoms. Okay, so this is not a tool that dictates you what to do. It's really a tool that just gives you information, and it's up to you to bring a diagnostic on top of those information. That will be all for this lecture. You're going to practice more during this week tutorial, and we really encourage you to apply this kind of tooling to your project, like the mesh generation or the terrain generation that you're going to do after reading week, because that will be really helpful for you to kind of like get some classical errors, find a way to fix them, identify stuff, look at how good or bad your quality is evolving. So it's really important for you to work on that, and we really encourage you to do this. Thank you very much for your attention, and I wish you a very good week.